Hi everyone, my name is Pritam Dey and I will be talking about parameter estimation for stochastic differential equations. And this is my video entry for the Math 545 final project. So without further ado, let me start. Stochastic differential equations, or SDEs, are often used for modeling different real-world phenomena in several fields like finance, biology, and engineering. So these are four explicit examples of SDEs which are often used in applied fields. So the first one is the Ornstein-Uhlenbeck process, which we know very well by now because it has been featured in several homeworks in this course. So it is used in evolutionary biology and for modeling interest rates in financial applications. Then there is the geometric Brownian motion, which we are also familiar with because it's used in finance to model stock prices in the extremely famous Black-Scholes model. Two other stochastic differential equations which I introduced here are like the stochastic logistic model, which is used to model population dynamics, and the square root process, which is very useful for many engineering and finance applications. So now I will describe the problem that I'm trying to describe here. So in practical applications, many times we do not know the particular value of the parameters, but we know the parametric form of the SDE. For example, consider this general SDE, which is given here, which has its drift and diffusion terms, both depending on the unknown parameter vector theta. And here we have available experimental data at certain time points. And we need to use these available experimental data to estimate the value of theta. So the first thing that we do is use the likelihood. By likelihood, I mean the probability density function of the observed data, but seen as a function of the parameters. So it is this thing here. And this, by the Markov property of the diffusion SDEs, the likelihood can be refactored, factored into a bunch of conditional densities where the conditional distribution of like the value of the process at one time point just depends on the time point which we observe immediately preceding it. These conditional densities are used in this expression here are called transition densities. And we'll be looking a little bit more into those in the next slide. So another quantity of interest is the negative logarithm of the likelihood. Okay. So an immensely popular SDE, as I mentioned earlier, is the Ornstein-Uhlenbeck process. And this is the process. So it has two unknown parameters. And suppose we assume that it is observed at equally spaced time points at T1, T2, and till Tk. And then suppose we integrate the equation from Tk to Tk plus 1, it yields this thing. And it is just the solution of the equation. And now this immediately implies that the transition densities are Gaussian. Specifically, it is this Gaussian here. Okay. Since now we have a closed form for the likelihood function in terms of the parameters, we can just estimate the parameters using several different approaches. For example, the maximum likelihood estimation method is simply the maxima of the likelihood or the point where the value of theta which minimizes the negative logarithm of the likelihood is also equivalent to it. So next, the other thing is the maxima a posteriori estimate, which is used in a Bayesian setting, where if we have a prior on theta, which represents like our prior belief on where theta lies. So then the maxima a posteriori estimate or the MAP estimate is simply very much like the maximum likelihood estimate, but except there is a small correction term, which is the prior. And then there are Monte Carlo based approaches. In Bayesian settings, Monte Carlo based approaches are very popular, and we simulate the observations from the posterior density of theta, which is nothing but it's a distribution which has density proportional to the likelihood times the prior density. So likelihood-based approaches, as I mentioned in the previous two slides, have a major challenge that most SDEs do not fall in the very restrictive family of SDEs called linear SDEs, where the Ornstein-Uhlenbeck SDE falls. And for those linear SDEs, we have Gaussian transition densities, but in general, it may be extremely difficult to get transition densities for SDE which is not linear. And this is because the transition densities is a solution to the Fokker-Planck equation, which is also known as the Kolmogorov forward equation. And these equations are generally intractable for general SDEs. And hence we need to approximate the problem in some way to get an approximate solution. And one way of doing that is by using the Euler-Maruyama method, which is a numerical method for approximately simulating SDEs using steps of the form this here, where this increment in the standard Brownian motion part is just a normal distribution with the time difference as the variance. So under this approximation, we can get an approximate transition density, which is Gaussian, and it has this form over here. This method is simple to implement, but it has a major disadvantage that if the Euler-Maruyama approximation is bad, then this method is equally bad. Then we can get better approximations, probably using better SDE discretization methods, such as the Milstein method or higher order Ito-Taylor expansion-based methods. But these are not mentioned in this, like we will not be going into detail in this video. So this is a illustration of how different the exact posterior and approximate posterior from Euler-Maruyama approximation can be for the Ornstein-Uhlenbeck process. And here you can see subtle differences between these two distributions. Like I can see there is a slight in the exact posterior distribution, there is a slight trend of Q being increasing with lambda. But that is not visible in the approximate case. And yeah, there are subtle differences, but they are almost similar. So let us look at the point estimates. The point estimates of the in the case of the like the Euler-Maruyama based approximation and the exact one are very close, as you can see, like 0.77 versus 0.8 and 0.91 versus 0.99, which is like pretty close. So next, we look at another way of approximating the likelihood. So instead of just going in and trying to discretize the SDE, you can try to just approximate the transition density and using a Gaussian thing. So one way to do that is like moment matching. So what we do is, like, while the Fokker-Planck equation is difficult to solve, suppose we just assume that the solution is a Gaussian with a time-dependent mean and covariance function, then that allows us to get like ordinary differential equations for the mean and the covariance. And then using the like solving those ordinary differential equations gives us approximate means and covariances for the transition densities. So these methods are like very rough kind of thing, because like if the transition densities are very un-Gaussian, for example, like they are multimodal or highly skewed, then this method does not work very well. So since my time is nearly up, I would just mention that there are several other classes of methods for parameter estimation, which includes like discretizing the Fokker-Planck equations with forward difference equations, which we can imagine works great as well. And then there is the estimating function-based methods, which are generalization of likelihood methods, and then there is a generalized method of moments methods, which are based on like generalizing the moment matching that I talked about earlier. So that's it. Thank you for your attention.